Tonight, we are going to hear from David Porris about using virtual math manipulatives. Would everyone please introduce themselves in the chat window, telling us what you teach, where, and what your Twitter handle is, if you have one. Again, I'm Rana Arshid Hafiz, and before I introduce our speaker, I'd like to explain how these meetings work. These meetings are recorded and are available within 24 hours after the meeting ends. To view the recording, you can use the same link you used to get here tonight. The global math community prides itself on being friendly and supportive. The chat room is available for topical and general conversation throughout the meeting. I'll be sure to catch your questions for the presenter to be addressed at the end of the presentation. Our speaker tonight is David Porris, and I'll let David introduce himself to us.
Thank you so much. It is a real honor and pleasure to be talking with all these educators from around the world as part of the Global Math Department. So thanks for joining tonight. My name is David Poras. I'm a 6th and 7th grade math teacher. This year, just teaching 7th grade math in Weston Middle School in Weston, Massachusetts, outside of Austin. I live in Newton, Massachusetts. I've been in teaching middle school math for over 20 years now. I think I'm on year 22. And I work on the content team at Mathagon as well. So I'm going to be sharing some ideas about how to use virtual tools to help engage students in mathematical exploration and discovery. I'll be using the tools on Mathagon, which are free for students and teachers around the world. I stumbled across Mathagon about a year and a half ago as I was looking for ways to enhance and excite my students in mathematics. And I think it's a really nice tool. Again, free for everyone. So no Mathagon sales pitch here tonight, but I want to share a few ways that I've used the tools to really help students, again, explore and discover mathematics. There's lots of things on Mathagon. One is Polypad. I'm going to be spending our time on Polypad tonight, where the virtual manipulatives are. So I'm just going to go to a blank canvas under File, just a new canvas, just to give myself an open space. I think of the canvas as just an open space for students to explore and play with mathematics. At some point later on in the webinar, I'll show you where you can find tutorials and old webinars on Mathagon, but I just want to dive into the math here tonight first. So I was thinking about how I used to teach area of a circle to my students when I first started teaching many years ago, and I cringe at what I was doing. As I'm describing this, maybe if you're brave enough to put in the chat a lesson that you think back on how you taught it years ago or last week. I have lessons that I taught last week or this week that I know next time I'll do very different. But I'm going to focus on how I thought about the area of a circle. We know it's pi r squared. When I first started teaching, I would just put the formula on the board, and kids would practice finding the area of lots of circles. And I would challenge them by sometimes giving them the diameter or sometimes giving them hard numbers to work with. And I don't recall if kids ever asked me questions as to why the formula works or where it comes from. I don't remember my answer. I'm sure it wasn't a very satisfying one. That didn't last too long. And then I began to, on my own, I never really knew where that formula came from. I'm sure I learned it in school, but I didn't recall. And so as my interest as a math teacher, I went and thought about and sure went online or talked to my colleagues about where the formula comes from. And I came up with this whole story about how I ordered a pizza, and you've all thought of these stories, and took the pieces from the pizza and had to put them onto a baking sheet that was in the shape of a rectangle. And I drew all these pictures on the board and proved the formula. And I think it was fun for kids because I hammed up the story a little bit and maybe brought in a pizza from time to time. But again, it was them watching me tell this story, and they might have done it in their notebook and copied it down. And at least maybe they took away from that there was some logic behind where the formula comes from. But if I'm being honest with myself, they didn't really own that idea. And so then a couple years later, I'm not sure when, there's lots of animations out there on the web that show great visuals of that process. There's one on Mathagon, which I'll share with you. It's in a Mathagon course. The Introduction to the Circles in Pi course. It's got a triangle that you can play. It's got a slider going back and forth. You can change the number of pieces, all sorts of fun. But even like when students are doing this, they're still kind of watching it happen and not really doing it for themselves. So I've shared this with kids, but I want to share tonight what I did last year that I felt like really took this idea and allowed students to build their own knowledge. Now, this was after I had done area of parallelograms where we had cut off the parallelogram and made it into a rectangle, and done the area of triangles where they take the triangle and make it into a parallelogram or into a rectangle. So we had really like built up the idea. Thank you for putting the links in the chat. We had built up the idea that taking a shape and trying to form it into a rectangle can help us prove the formula. So I just told my students to go build a circle on Polypad and see what they could do. And the exploration and discovery was great. Now, this again, my students last year had played on Polypad a lot. So I'm going to demo it on the webinar tonight. But as a teacher, I really just allowed kids to go. And yes, I was checking in and I was helping and doing all sort of the teacher moves. But let me just share with you how I did this and how I think it really helps students build their own knowledge by not watching me tell a story, even if it's a fun story, not watching an animation that another person made that might be a really nice visual, but actually doing it for themselves. And that's the power of these virtual tools where students, I think, can build their own knowledge by engaging with the manipulatives themselves. So I'm going to go to the fraction circles here. Again, there are tutorials on Mathagon that I will show you later in the webinar. This might feel kind of quick, but I just want to get to the math and not focus so much on the tool right away. So I'm going to take this fraction circle of a 6. There's a copy button at the bottom. I'm also just doing the C button on my keyboard to make 6 of them. And I'm stacking them up like this. So when I spin them around, it just makes the circle really nicely. So I'm going to make a circle with 6 of these pieces. I don't need the labels here, so I'm going to go over into settings and turn off the number labels. So there's my pizza. And I first might like start having a conversation with kids about if this tile has an area of 1, what's the area of that circle? And I just said, first, go make an estimate of the area of the circle. This was actually the introduction to the activity. And they took the square and they copied the square a bunch and tried to make an estimate of the area of the circle in those squares. And again, they understood the concept of area, but just having them do this on their own was kind of a good hook to the lesson of making an estimate of the area of the circle, as well as a reminder of the concept of area. So they came up with an estimate. They shared it with the class. We had it up on the board. And then we had talked about the process that we had used to find the area of a parallelogram and the area of a triangle by making things into a rectangle. And I just said, go. But certainly a number of students were independent on their own. Some needed support. But what I want to show you is what these students did. And so I'm going to take these pieces and arrange them into a parallelogram-ish. So there's the parallelogram-ish. I've taken those 6 pieces. I've put them on my cookie sheet, as I've done in the past on the board. But here students are doing it for themselves. And now in polygons, there's this shape here, which is a custom polygon, which right now is a pentagon. If I click on a vertex, it'll go away. So now it's a quadrilateral, and it snaps in place. So as I put it on top of this shape, you can see that kind of snaps to the corner here. This one will snap to the corner. I can drag it over. And so students were doing this themselves, where they put the parallelogram on top of this shape. I can change the color down here to make it kind of semi-transparent. And there's the parallelogram. That's a good-ish estimate of the area of the circle. I'll take this parallelogram and copy it down here. And now if students need a little support there, now they were off and running. And again, this was because of the foundational work that we had done around area of parallelograms, as well as the tools on Polypad. So on Polypad, what we had done, I'm going to fix the vertices here so I don't move a vertex by mistake. I fix the vertices. I'm going to go get a straight edge. Here's a ruler. It snaps to these points. It'll snap to a 90-degree angle. And I'm going to click on the polygon and cut it. So there's a cut feature down here. Again, students have done this a lot as we were exploring area of parallelograms. So I can cut it, get the ruler out of the way, and there's the rectangle, which is really nice. I'll copy this whole thing, and there's a join button down here at the bottom. I'm going to join these 2 pieces together to make a rectangle. And now we can explore the area of that rectangle and compare it to the area of the circle. So to do that, I'm going to construct a rectangle around the green rectangle with the line tool at the bottom. There some construction tools. So I'll do this in black so we can see it a little bit better. And I'm going to build this rectangle. Let me just draw the rectangle around it. There we go. I'll move the green one out of the way. And if I click and drag on that rectangle and click on these three arrows, I can see that Polygon has calculated the area of that rectangle as 10.4. And if students didn't believe, or if I asked them to check, here is one. I'm going to copy a bunch of them to make 10.4 of them, just to check that the area of that is 10.4, just to kind of build some understanding with students, some buy-in that actually is 10.4. I'll cut this in half-ish, maybe that's about 0.4, and then I can take all these and put them in the rectangle and see if it takes about 10.4 of them to fill in. So there we go. I'm going to cut all those, cut all the way across. So I have these pieces that I can put in over here, and I'm filling in and hoping that about 10.4 fills in this shape. I could cut that a little bit more if I wanted to. I'm going to stop there. You can get the idea. I could cut that and I could put it in, but it seems like the area of that rectangle is indeed about 10.4 square units. Now in the construction tool, I'm going to build a circle around the fraction circle. It snaps in place. I'll move the circle down here. I actually wanted to label this, that this area is 10.4 squares units. And then we'll see the area of the circle. And I click on these three dots, and the area of the circle is 12.6. And certainly now a great conversation in the class as to why the area is not the same, right? What happened in this process that caused the area of the rectangle not to be the same as the area of the circle? And certainly it's those pieces that weren't part of the parallelogram. If I was doing this in class with students who hadn't explored on Polypad before, maybe this whole one I would do as an example first. They'd be doing it at the same time. And then I'd say, how could you make this better? And then have them go off and try to make it better. And certainly if you cut the circle into more pieces, maybe with a fraction bar of 12ths or 10ths or 11ths, that will have a smaller amount of crust almost on the outside. So for the power of the webinar, I have done one here. So I have all my folders here. I'm going to pull this up. This was one with 12ths. And you can see with 12ths here is the exact same process. Again, students would be doing this, right? Students would be moving the pieces over. Students would be constructing the parallelogram on top. Students would be cutting it. Students would be finding the area of the rectangle, comparing it to the area of the square. It's much closer, right? It's 12.6 and 12. If students wanted to, they could build a really big circle like this, not using the pieces of the fraction circle, and they could split that big circle into any number of pieces. I'm going to go to the measuring tool and put a protractor in here. This also snaps in place. It can fill up the circle, and then I can use the line tool to cut this circle into a number of pieces. So I could go like that. It's all snapping in place here. I'm going right through the middle and snapping to the circle. What's this? 10, 20, 30, 40. There's 45. And then I can get the protractor out of the way. Oops, I don't want that line. I can get the protractor out of the way. And then I can use the custom polygon tool to then make all those pieces, unlike with the fraction bars. And here, if I click on this line, it adds a point, and I can add any number of points to try to like round this piece out. And I had students enjoy this part of the process more because they actually made huge circles on there, and they added lots of points here to make this as circular, as rounded as possible. And then fix the vertices, and I can take this and spin it and copy it and spin it around. And there we're off and running with the parallelogram. I got to rotate that a little bit more. But again, this went from students watching me do it, students listening to some story I told, students watching a cool animation that's really, really well done, to actually doing it themselves. And when they're doing it themselves, they're seeing how the pieces fit together. And then as a class, we all came together and talked about, okay, in general, how can we get those little pieces as small as possible by cutting it into more and more and more pieces, infinite amount of pieces, get it to the area of the circle. And then what was really nice to take this rectangle and say, where does that show up in the circle? Well, here, the bottom of the rectangle is all the yellow pieces. So that's half of the circumference. So I can add that in here as half of the circumference. And then I can take this rectangle and move it back here, and we see it matches up right with the radius. So then I can add another text box saying this is the radius. And in fact, I had a couple of students last year who, despite then we went through the algebra and talked about how that simplifies to pi r squared, because that's what you'll see. And that's what, if you Google the formula, that might come up. And it's a simplified formula. And, we talked about the value of having a formula inside a formula. But there were a couple of students who every time they found the area of the circle, they did half circumference times radius, which actually was so joyful, for me to see that the power of this lesson stuck with them, that they visualized the circle forming this rectangle that had dimensions of half circumference times the radius. And it kind of makes me want to consider going forward, not telling them about pi r squared, just saying this is the formula and go with it. On assessments, back in the day when I first started teaching, I would never ask questions on assessments about where formulas come from or what we did in class to get the formula. Students could describe this process, right? And so I think there was great power for them in doing this themselves and then understanding. They might not have a memory of all the details of where this came from, but their big takeaway is that this formula came from a process, right? And that process was the same process we did with parallelograms. It was the same process that we did with triangles. And in fact, later in the year, when we do volume of a sphere and we split the sphere up into square-based pyramids and we arrange those into a shape to find the volume of that, it all connects, right? And so I think there's great power in that all connecting. So that is one example of where I think virtual tools can really add a lot of value for students, just playing and exploring. Another example that I want to share, I have a hard time with a good visual of what 2D shapes fold to form nets. I've gotten better over the years as a math teacher as I've practiced more, but I really do have a hard time in my head with a good visual of how 2D shapes fold together from a net to make a 3D shape. And so here's another example where I think a virtual tool can be really helpful. So I'm going to put 4 of these squares on the screen. I'm going to click and drag to select all of them. And one of the options on PolyPad is fold the net. So you can see down here at the bottom, I'm going to click fold net and it folds together. Now that has a top and bottom that are missing, but I can see, and students can see that folded together to make a net. I can stop along the way and I can rotate it and really see what is happening as I unfold and fold that. If I click unfold, it goes back to the individual pieces, and I could put a couple other squares and fold the net, and there's the cube. And then it's just, okay, students, go play with squares, see what happens, right? And they just go build and explore. This feature was new this summer, so I don't have examples of how I did this with students over the past school year, but I've showed it to them a little bit, and they're just going to build things and exploring and going, allowing kids just to play and discover as they build these is really exciting. If I put 6 in a row, you might have a prediction as to what might happen when there's 6. I'm going to ask you some questions in the chat in a second, but let me just show you what happens with 6. I can fold those together. There's some overlapping going on, right? So those squares, as they fold together, overlap right there. But if I put a hexagon on and then fold them, I have to unfold this to get it all the pieces. And now I fold them. There's the prism without the bottom or the top. So that's really cool. I want to show you a class opener that we have in PolyPad to help engage your students on this idea. So I'm going to go to the task page. If you're on Mathagon and you click on For Teachers, that shows up if you have a teacher account. Again, all of this is free, but you can also just go to mathagon.org/teachers. And one of the links on the teacher page is to lesson plans. And so I clicked on the lesson plans, and I'm going to go to the one called Class Openers and Math Talks. So this is a growing page of things you could do with students at the start of class, either as an opener or as a math talk. And one that we have here, I'm going to scroll down a little ways, is Unfolding Nets. So I'm going to pull this up, and I'll give you a minute and pick, thank you for putting the link in there, pick one or two and describe in the chat what you think is going to happen when I click Fold Net. So the blue one, I think I just did one. What's going to happen on the orange one? Is that what's going to happen on the green one and the red one and the purple one? Try to visualize what's going to happen as those fold together. It might be hard to put into words what the shape is going to make, but let's take 30 seconds of me not talking and try to describe what you think might happen in the chat with any of those colors. Purple, orange, green, red, or sorry, blue, blue, orange, green, red, purple, peach. And drop any ideas in the chat, and then I'll fold them in 30 seconds or so. You can go do it yourself at mathagon.org/teachers. Thanks, Ralph. You think the orange is going to make a box? Awesome. You think the green one will be an open box with the two top squares overlapping? Cool. Green is an open box. Awesome. You agree about the green? Yeah, cool. Awesome. Thanks for participating, everyone. Nice to see the ideas. Part of here is trying to figure out like the algorithm that is going on and how they're going to fold. That one when I showed you with the 6 blue squares that didn't connect, they overlapped until there was a hexagon, and then it went from there. Let's do it. All right, so the blue one, I think we all, if there were answers, that makes the cube. The orange one also makes the cube. And just a great task for students, go find all the ways to make a cube, and just go let them build with the squares and do it is a really fun task for students. Can they find all the ones that make a cube? The green one, here's the green one. It is like an open box, but those connect and there's no overlapping going on the algorithm as to how those come together. Here's the red one, kind of like the same with the front and back. I might have missed some on the purple. Any predictions on the purple one? I know that was the hardest one for me to visualize. When you fold this, it says it's not a net. That can't fold. And so what a great thing for students to explore. Why can that not fold? I've seen a couple of my students and my kids. I have a 6th grader and a 3rd grader. And when this feature came out over the summer, they just love trying to build things. And most of the things they built initially couldn't fold. And what great thought process for them as they were problem solving it. Why isn't that folding? What's happening here that causes that not to fold? And then here's the peach one. Shoot, there is some overlapping there, right? Yeah, it's a great thinking task, right? To start and then confirm with this activity, like actually folding, right? So that's pretty cool. What I just want to share, we're going to move on in the nets. I've been exploring only one with cubes, but there are, dodecahedrons that you can unfold. So there's some that are pre-made here. Icosahedrons are pre-made. This black tab can move them around the screen. So those are the Platonic solids. And then in every Mathagon account under file are some pre-made canvases. These are all mine here. But under examples and templates under geometry are all the Archimedean solids. So I'm going to go back to this one. And these are just like wild to unfold and fold. So look at that. It's so cool. Rhombocosadodecahedron might be the right pronunciation of that. So we could spend just a whole hour talking about these, but I'm gonna move on because let's just do another math task together here. And I'm gonna go to the one that is what are the 2 cards? So this is I've done this a few times at the start of class, had a lot of fun with students. I'm gonna take all these cards and turn them over so you can't see them anymore. I'm gonna stack them. I'm gonna shuffle them a few times so the cards are being shuffled. I'm going to double click here to put one card on the scale. Double click to put another card on the scale. Make a random prediction in the chat. What do you think the 2 cards are? Let's see. It was the cards 1 through 10. I shuffled them up. Let's just hear some random guesses in the chat. This is what I would do with students. Make a guess. 2 and 3. Thank you, GMD host coordinator. Good guess of 2 and 3. Anyone else want a big prize if you get it right? I don't know what the prize is yet, but your pride in the in the Global Math Department webinar. Awesome, Ralph, thank you, 10. Yeah, so then what I would do with students as they make their guess 3 and 5, 1 and 6, awesome. I might take the 5 and put it on the scale, and oh, see, these 2 cards are heavier than 5. And depending on the scaffolds that I wanted to do with students, I could put this up here and slide it over to show that it is more than 5. Maybe I'll stick this 2 on the scale. Oh, it's still more than 7. So I could slide this over. Feel free to adjust your guesses in the chat. But now I'm going to roll the dice and see what happens. What do we got? More than 2. We knew that already. More than 5. We knew that already. More than 5. One more before I put on the third dice. Oh, it's more than 9. So now I can put that on here. Feel free to adjust your guess in the chat. I'm not going to be checking them all out. But now I can put a third one on. There we go. Oh, and it became less than, what do we got here? Less than 13. So now we know it's between 9 and 13. And now students, we could have really pause here and have a great conversation. Maybe students could list all the possibilities. Maybe I could roll the dice again, see if that gives us any more information. Oh, it is heavier than 8. We already knew that, and so on. In the interest of time, I'll do a couple more and then stop. What do we got here? Oh, more than 10. That's exciting, right? And I'm doing all the thinking for us. I am seeing some good things in the chat. But let's compare it to 11. So maybe now we want some more information. I'm going to go to the number cards and just put 11 out here and get rid of the dice, and let's see if 11 balances it. It didn't. Let's see if it's 12. It balances to 12. So now we could have students continue, right? What are all the choices that can get it to be 12 and make that list and talk about it? And then eventually I might reveal one card. And then I think we all know the other card now, right? 2. Awesome. Yeah. But just like really quick, it is there in the task page. You're ready to go. Good 5 minutes to start a class. Students thinking about the equality of that, the balancing of that, I think is a nice use of these virtual tools. But let's keep going with the agenda. That was just kind of a fun aside that I wanted to do. I want to spend some time on the balance scale because I think the idea of equality for students and different representations of numbers is another example where a virtual tool can really help propel students like structures in their head of equality and of number. So in the task page again, which if you just go to mathagon.org/teachers, mathagon.org/teachers and go to the lesson plans. One of the lesson plans right at the top is balance scale polypads. You can also get here, I'm going to put this in the chat, mathagon.org/tasks. Will take you right to this page that I'm on right now. And there's a number of balance scale polypads that I'm going to share with you tonight to talk about how these, again, can, I think, help students like create meaning for themselves as they're doing something. So this is one where it says balance the bottom scale. Now this has an answer here. This says the answer is 8 because I made this in my teacher account and you're seeing it in my account right now. If I copy this link and open a incognito browser and paste it in, this is what a student would see. If you went to mathagon.org/tasks and opened this, what you would see is a question mark here as well. So I gave this to my 3rd grader over the summer, or I think it was last spring even, and she just went to the numbers. She was kind of familiar with Polypad, and she said, I'm going to try 5. So she went over here and went 5, and she kind of, without even doing anything, was counting by 5s and got to 20. She was in 2nd grade at the time, was like, oh, that's too small. And then she counted by 6. She knew that when you put the 6s on top of each other, it's going to add those number cards. And then I think she might have tried 7 next, but eventually she got to 8 and she put the 8s on top of each other and saw, oh, that was 32. And again, without like talking about counting by a number or what the multiples of 8 are, she just went and did it and was putting the 8s on top of each other and saw that 4 8s got to 32. And then she went over here and put 3 8s on the scale and balanced it, right? And put those 8s together to make 24, which I thought was a really nice, just like quick, intro task to help students think about 4 of something is 32. What do I need to balance it if I have 3 of something? And if they put 8 here and get it right, there's this nice confetti that comes down the screen. There's a video on how to do this if you're interested. I'm going to go back from the incognito browser and go back to the task page. I just have a number of different examples here to share about how I think the balance scale can be really helpful. Here's one where it uses many of the number representations that we have on Polypad. So there are number tiles. There are these number bars and frames. These are like the Cuisenaire rods, the number frames. We have the number cards that we saw. I'll show you the prime factor circles in a minute. But the task here for students is just balance these scales any way you want, right? So here, students might see that as a group of 10. They could put a 10 on top of it to see. And they might say, oh, that's 23. Here's 6. How do I get that to 23? Well, maybe they would go to the number frame and put a 4 here to make it 10. And then take that and copy it if they wanted to, and then get a 3. And that's going to balance the scale. So I think this is really nice for students, that all the visual representation of numbers can work on the scale at the same time. And then students can save their work. As a teacher, you could decide which ones to share with the class. And what great rich conversation can happen about what tools what tiles, what virtual tools they chose to balance the scale can be a really great conversation to have. I'm going to show you some more up the scale here in linear equations. This is an example of an equation that is balanced with the algebra tiles. And so I've had great success in using this with kids for as long as they need to. What I think is really wonderful about these virtual tools is students feel safe in using all the manipulatives until they don't need them anymore. And there were some students last year, if I gave them an equation on paper, an abstract equation, they went to Polypad and they built it. They built the equation in Polypad and they used the tools I'm about to show you to keep the equation balanced as they tried to find the value of the unknown. I've shared a story over some past webinars where, like many of you, I'm sure I've used integer chips for many years in my classroom, the positive and negative chips. And I had them in Ziploc baggies, and we would do a day or two of working with the chips. And then I felt like we'd be ready to move on to more abstract thinking without using the chips. And I'd put them on the shelf, though, and I'd say to kids, anytime you want to get the chips, go get them, right? If they're still helpful, you can always use them on quizzes, on tests. I don't care, use the chips. And nobody ever did, right? Maybe it's in middle school, like the social pressures of feeling like that's not a more advanced way to think mathematically, despite my greatest efforts to make a safe environment where we all learn at different ways and these tools can be helpful. And part of it was on me for not allowing time enough in class to use the chips. These virtual tools, maybe it's they're engaging, maybe there's the safety behind a device. I found that kids would go and use them until they didn't need them anymore, right? So here, kids would go to the number cards and maybe by mistake, they would say, I'm going to add on 22 here, add 22 to both sides. Now, when you add that to both sides, does it maintain equality? Yeah, it sure does. It didn't maybe help us down our path, but it maintained equality. And they might say, oh, what I meant to do was add the opposite of that. So if they had negative 44 to each side of the equation, and then put that here, does that stay balanced? Yeah, it sure does. And then here's a 0 pair, right? So now I really like here that it made a 0, not a 0 pair, just made a 0. But now students have to take the 0 off the scale, right? So that doesn't just disappear, but students have to actually say, okay, let me get rid of that 0. And now I have 2 of the negative x's. So I'll go to the algebra tiles and add on 2 of the x's, right? But if I do that on one side, and we want to balance the scale, let me copy those and put them on the other, right? And now it's balanced. And again, I can put those on top and make a 0 pair, and those go away. Now that's 70. Students are tempted here to do this. That didn't balance the scale, right? When I move the 70 over, it doesn't automatically become positive 70. Students need to go through the process of thinking, what do I need to do here so that negative 70 becomes a 0? Well, let's put a 70 on each side of the scale. And that visual of whether the scale is being balanced or not, I think is really powerful for kids. So there's the 0. Now, students might know what 70 divided by 5 is. They can pull out a calculator, but I just want to take this opportunity to show off the prime factor circles here on Polypad. If you've played the game Prime Climb, you're familiar with Dan Finkel's work at Math for Love. These are obviously built in collaboration with Dan Finkel. And so I can take the number 70 And you may know that the orange is the 2, purple is the 7, the blue is the 5. But what's really wonderful about the prime factor circles, I'm going to copy the 70. I can pull these out. So they are like interactive prime factor circles. So I pull out the 5 and we see that 70 became 5 times 14. So this for some students is almost quicker than going to grab a calculator and divide by 5. They just put the 70 on the canvas and pull out a 5 and say, oh, if I divide that by 5, that is 14. There it is. We balanced the scale. I could spend a whole webinar just talking about factors and multiples with these prime factor circles, building the Venn diagrams and GCF and LCM, just with the ability to pull those apart. Let me do one more example of the balance scale as we're building up the ladder of equations that students might solve. Let's just go all the way down to the bottom one, a quadratic equation. So here, again, in the algebra tiles, students would go through, I need to add an x squared. Yeah, those circles can separate is so cool. So I'll put an x squared on each side. I'm going to show you another example here, Kristen, of how those circles separate. I got my 0 pair, so I will take this 0 pair and get rid of it. I'll go to the number cards and get my negative 32 to add to each side. But I'm doing this one for another example of the prime factor circles because I think that is a situation where the virtual tool adds a lot of value for students being able to actually pull those prime factors apart or any factors apart and put them back together. So now I'm going to go to the prime factor circles. You can type in any number you want. Here's 588. So the first thing that we want to do with 588 is split it up into 3 groups. 3 is the green. So I'll pull out the 3. So that tells me that one of these is 196. So I can just get rid of the 588 and put on the 196. But these prime factor circles are also great for thinking about what times itself is 196. So I could go to the algebra tiles and I could show the square here, right? That what we're trying to find is what value of x is going to make that square. We could talk about that. Let me get those off the scale. But here we can take the number 196 and think about what times itself is 196. I can pull it apart and in one group have a 2 and the 14, and there's the other 14. And we see that the square root of 196 is 14, which means one of the x's is 14. So cool. Now, this is a mess of a polypad right now, which is great as students are first exploring. Eventually, as I was talking about, I would have the algebra on the screen matching up what's happening on the, on the scale so they can keep track of the steps that they're doing. Another great use of the prime factor circle is just talking about what makes a square number, right? How can you tell from a number here, if I put 1,000 out here, is 1,000 a square number? Some students might think it's a square number. Can you split them into 2 equal piles? Right, we can do a 2 and a 2 and a 5 and a 5. Oh, but there's this I can't. It's a cube number, we know, but shows us nicely not a square number. So that's super cool. I'm going to keep going because I only got 10 minutes left and I have other things that I want to share. But I do want to take this quick moment to show you more on the teacher page here. The purpose of tonight is how to use virtual tools to engage students in mathematics. I'm sharing some things on Mathagon, Polypad, which is the virtual manipulatives on Mathagon, free for everyone, right? Free for teachers and students. If you're interested in learning more about how to use the tools on Polypad, there are lots of webinars here that you could go explore. There are tutorials. There are videos on how to make classes, how to add students, all that stuff from the teacher side of things. And then on Polypad, there's a link to tutorials here as well, which brings you to a tutorial on each one of the aspects of Polypad, how to use the geometry tools, how to use the balance scale. So you can go explore that at your heart's content. But let me move on to our probability tools, because here's another example where I think the virtual tools can really help advance students' thinking and understanding of things. So I'm going to go to a new canvas. I'm going to go to tiles. I'm going to pull up some dice here. Let me zoom in a little bit. I'm going to put 4 on the screen. And I'm going to do this 5 times. Quick question for you in the chat. I'm going to spin all the dice. That was once. I got 1, 1, 3, 5. I'm going to do it 6 times. How many of the 6 times do you think will I get at least 1 6? So I didn't get any 6s right here. Put that in the chat. Quick guess. how many of the 6 times that I'm going to spin these 4 dice do you think I'm going to get at least 1 6? I'll give you 10 seconds to drop a question in the chat, or drop your prediction in the chat if you'd like to. Awesome. 2, 5, 4. Great. I'm getting some polypad questions. I will answer all those at the end of the webinar. Thank you, Kelly, for that question. Awesome. Yeah, thanks for the answer. All right, let's do it. Let's see. We are no 6s, 0 for 1. 1 6, 1 for 2. 2 6s. What's that? 2 for 3. No 6s, 2 for 4. 2 for 5. And the last one is, yeah, half the time. Awesome. So 3 out of the 6 times I got some 6s. And what then? Now, this in class, I'd actually do this with big dice. I have big dice and we roll them, and then I'll have students, kind of play it on their own and explore. This is a famous question in the history of probability. Chevalier de Mere was a French, he was a lawyer or an amateur mathematician, and he explored this game. Where's my probability webinar? And this is a canvas that I made and I shared with my students. It was a really easy canvas to make. I took those 4 dice, copy, paste the whole way through. But I wanted students to get a lot of data on this activity. So each student got a set of 20 of these 4 dice, and they could spin them. It's just kind of fun to see. And they could go through and count how many times they got at least 1 6 out of these 20. And I think so then I had students do it in class. They collected a lot of data, right? If they had actual dice, they could get some data and we could record that data. But in one class, I have a Google sheet of the data. I had 25 students. They each did that canvas 20 times. So I each had them do, I got too many tabs here. Was it this one? Nope. It'll be the last one, of course, right? Yeah, of course, it'll be the last one. I had them do this 20 times, and they collected a lot of data. So, and that meant every student did it 400 times, which meant as a class, within like 7 minutes, we got 10,000 trials of spinning 4 dice. Now, there are lots of sites where you can like program it and you can just get a list of the results. But here, when students saw the actual dice being rolled and they knew their classmates were doing it, there was a sense of belief that this was the actual data, right? You could write a program, where you could get the actual number, but they saw in their 10,000 trials, there was at least 1 6, 5,215 times. And I think they really believed that. I don't have time tonight to go into then how we developed the actual probability of this, the theoretical probability, but when it's a pretty intense calculation for a 7th grade student. But the power of this, when we calculated this was the theoretical probability and it was 0.5177 and compared it to the experimental probability, they believed the theoretical probability. Over 10,000 trials that happened really quick and they saw it. It matched up really close with the experimental probability, which I think was really powerful for kids. And then in the story, when when he was first playing this, he thought he would win about 2/3 of the time because he thought this has a 1 in 6 chance of getting a 6. This has a 1 in 6 chance. This has a 1 in 6 chance. And this has a 1 in 6 chance. So he added those probabilities and got 4 6, which was 2/3. Not correct, but he won more often than he lost, if this is a fun math story, if you're not familiar with this. So he thought his probability calculations were correct because over the long term, he won money. So he was like, yes, I'm good. So his friends, I think, were kind of bummed out that they continued to lose money. So in his second game, he developed a new game where you'd roll 24 pairs of dice, like I have here on the screen. And if you get at least 1 double 6, then you're the winner. Here, I don't have any pairs of 6s. So I'm 0 for 1, and I didn't get any double 6s. I could do it again. He thought the same. There's a double 6, right? The same approach that he did in the first game, he applied here. The chance of getting a double 6 is 1 out of 36, and there's 24 of them. So he thought he would win 2/3 of the time. I had my students do it. We collected a whole lot of data, not quite as much, because here, this is one trial of this event, right? Where on the first one, every time I rolled those, they were 20 trials of it. So we didn't get as much data, but on my Google Sheet number 2, my one class did it 1,700 times, and 840 of them there was at least a 6, at least a pair of 6s, and 860 there weren't, which means our experimental probability was 0.494 and the theoretical was 0.491. And that's what actually started a lot of the probability conversations between him and Fermat and Pascal. He was losing money. He wasn't sure why. And so that kind of laid the groundwork for a lot of the thinking that we do in probability to calculate what the actual theoretical probability of this event is. But I was really struck how I've done this same lesson many times in the past where students would generate 50 examples of the game and they'd go play it. And I feel like even though we went through the really detailed calculations of the theoretical probability, and I feel like they got it, there was something so much more powerful when they could see that we as a class generated 10,000 examples of this, and these probabilities were really close to each other. So that was a powerful tool. And the last thing I want to share, and then I'll open it up for questions. I think I got 5 minutes here, is something on our task page. I'm going to go to mathagon.org/tasks. Yeah, we can leave this. And this task is called Perceptions of Likeliness. I'll put this link in the chat if you want to explore it on your own. You don't need to go here now. I'm just going to share with you how this works. So I made a Google form, which is in the lesson, where I asked students to rank from 0 to 100 what all these phrases mean. These are phrases that we hear a lot, out in society. Almost certainly, almost no chance, better than even, chances are slight. On a scale of 1 to 100, what do they think? This was a new lesson just in the past month, so I put it out on Twitter, got a lot of people to answer the survey. Some of you are probably those that answered, so thank you. Got some sample data, and I'm going to share with you the sample data because I think it's a great example of how virtual box and whisker plots can be really powerful for students. This is actually based on an article that you can read at the bottom by Rick Wicklund. So here's an article that is the basis of this lesson. But let me show you what I did with the data. So I'm going to go to Polypad. I'm in my files, data science, and likeliness ranking. Where's the sample data? There we are. All right. Here's all the data. Big table of data. In that lesson, I show you how to get the data from the Google form into Polypad. But what I want to talk about tonight is how, in the last couple minutes I have here, is attaching this to a box and whisker. So I've taught box and whiskers for years in school without great uses, great examples of virtual tools. So I'm going to go to chart, put the box and whisker on the screen. There's a blue tab on this table, which I'm going to just connect to the box and whisker. And there's the box and whisker plot of all that data. And I'll make it bigger. I know it might be a little bit hard to see over a webinar, but those are all the categories from, all this data is sorted from what the people that responded to my survey had as the most likely to happen, almost certainly at the top, and improbable down at the bottom. And I found in my teaching of box and whisker, even though there are some tools out there that could help students make a box and whisker, we got so bogged down in the quartiles and the medians and what it meant that it was hard to get to some really good conversation about what the graph is telling us. And so we don't have time in the webinar to do a notice and wonder here. Let me move this out of the way to make it a little bit bigger. But I was going to ask you to do some noticing and some wondering about this one. We can see some of the whiskers are really long. Right? They're on this probably not. This whisker of probably not goes all the way over 50%. One of the options on the box and whisker here is to toggle the outliers. You may recall that an outlier is 1.5 times the interquartile range from that thing from the upper quartile. So if I toggle the outliers, those become dots. So now we can have a great conversation about why is this line so long? Why is that whisker so long? Because there was one person that ranked probably not as 75, and we could probably think maybe they misread that. They thought that was probable. And then here is someone that said probable was in the 36. Maybe that was the same person that just misread probable and probably. But this is really interesting to me, and maybe not surprising when we see what these words are. Probable and probably are almost the exact same, right? And then we could talk about which phrase has the smallest box, right? The smallest one here looks looks to be likely. Why do we think that has the smallest one? Which one has the biggest one? Improbable. Look at all the range of answers on improbable. And then have a great conversation with students about, these phrases get used a lot. That article that is linked in the Polypad, I think it was talking about how these words get used in the military a lot in reports as people are deciding what type of action to take. And that the concern was that people were interpreting these words really differently, right? And if that's going to guide action to take, that should be a little more clear in what those words are. It is 9:50. I've talked way too fast, but hopefully there were some fun ideas shared about how you can explore these tools to help engage students in mathematics. A final plug, and then I will open it up to any questions that people have. On the teacher page, again, our past webinars on Mathagon, free for everyone, free for teachers, free for students. Students don't need an account to do work. If they want to save the work, they have to have an account. Go check out our tutorials. And the last thing to share on our events and webinars, we have a number of guest speakers coming to the Mathagon guest speaker series over the course of this year, starting with James Tanton in a week or so, Simon Singh, Sunil Singh's coming, Mary Kemper, Maria Del Rosario Zavala, Dan Finkel from Prime Climb, who I talked about, Catroni Ag, Desiree Harrison, and Jennifer Suh are joining the Mathagon guest speaker series. We're just going to share their mathematical brilliance with us. So hopefully you can make it to some of those. I'd love to see you there. I will stop talking and open it up to questions. I see some that are coming in the chat. So thank you for joining officially. I hope you found some ways that you could use these tools or other tools that are out there to get students to explore and make mathematics.
Thank you, David, for such a wonderful learning session this evening. I also want to remind all our participants that on October 5th, Vanessa Vicaria will be joining us and giving us a crash course on becoming a math therapist. Thank you so much, everyone, for joining us. And I hope, David, you'll be able to answer a few questions here.
I will happily stay on and answer any questions people have. Should I go through the chat and respond to the questions? Would that be best? Great. Yes, I am joining Teresa at the Mather Day this coming Saturday. So maybe I'll see some of you there. I hope it won't be too repetitive, Melissa. But there are certainly some themes that I'll be sharing that will be the same. So if you come join and it feels repetitive, I won't be offended if you if you back out. Interesting to see the interplay between Google Apps and Polypad in terms of classroom workflow. Yeah, there's a lot of good Google Classroom integration here. So again, under the For Teacher page under tutorial, there are some videos you can add. You can add students right through your classes in Google Classroom. You can assign Polypads into Google Classroom if you work in a Google Classroom school. So I am in a Google Classroom school, so I'm able to do that, and that has worked very seamlessly. I'm just going backwards up here. Will Mathagon always be free? That is 100% the intent of the company. We are a very small company that has a small team working really hard to put out new products and new tasks and new tile types. And there is a commitment that it's important to have high quality tools available for teachers and students around the world for free. So excited about that. There was a question about the iPad. So there is an iPad and a phone app that does work offline as well. So if you are somewhere where students might have not great access to the internet, or it's kind of spotty, and you have an iPad, there's also an Android app. Both the iPad and the Android apps work offline. There are some features that are not fully on the iPad or the Android app. So I think it's best to start off in Chrome, and all the features that I've showed tonight can work in any browser on any device. But there are Android and iOS apps as well. It is tough on a phone, right? With a small screen. There are times I've tried things on phone and it's just a little bit harder to get things to work out. Will it integrate with Microsoft Teams? That is on our roadmap of things to explore. I know that's something that folks have asked. So it is not on there yet, but something folks have asked about. So that's on the roadmap. Best place to get immediate answers to questions. Great question. So there is an FAQ on Mathagon. So that can be the first place. Go look at the frequently asked questions. That might be there. There is a community forum on Mathagon. So you could go to our community forum and ask any questions there. We are pretty active on Twitter. So I'm at David Porris, and I try to respond to questions people have. We are also Mathagon org on Twitter, not just at Mathagon org is a place to go. There is somewhere on the FAQ to, if you can't get your question answered, to fill out a support ticket. And we try to be pretty prompt in getting back to people's support questions as well. So those are the places to go. We do have a Mathagon Facebook page, not an active group yet. So I would say that Twitter, the FAQs, and our community page here would be the best places to go. Awesome. Yeah, it does connect really well to Google Classroom. Thanks for that, Kristen. Thanks for the feedback. So I have already, imported all my classes. I'm in my account on Mathagon right now. I'm not in my school account on Google, but you can see on my teacher dashboard here, I have some test classes that I've done in my webinars. I have my daughter in my test class here, right? But this really is, integrates really well on Google Classroom, on Polypad. If I have a Canvas that I've made, maybe I've made a balance scale one. This is one on fractional pieces. I could assign it into my class in Mathagon. And then so any student that is in that class would see that in their account. I also could assign it here right into Google Classroom. So that'll pop up as an assignment, and all the typical fields on Google Classroom would pop up on the screen as well. If I missed a question in the chat and you're waiting for me to answer it, if you want to retype it, I scrolled up and I think I got them all, but if you have any other questions that you want me to answer, I'd be happy to. All right.
Again, thank you so much, everyone, for joining us this evening. David, thank you so much for showing us all these fun tools on Mathagon. October 5th, we'll be back here with Vanessa Vicaria, and she'll give us a crash course in becoming a math therapist. So I'm sure that promises to be fun.
Awesome. And I'll just say a final thank you. It was a really honor to be part of the Global Math Department. I've been learning so much from all the newsletters for a while. I've attended a couple of the webinars, so really an honor for me to be here. Thank you for inviting me. Thank you for coming, everyone. I hope it was a good use of your time. And it was a real, as I said, treat and honor for me as well. So thanks very much.
Thank you. So I think we can about wrap up, David. I don't think we have any more questions.
Yeah, I think that was it. Thanks.
Have a good night. Have a good night, everyone. Thank you.
Good night. Thanks, David. And thanks, Rana, for hosting.
Thank you. Thanks, Lee. Bye-bye.
Bye.